Hello everybody, my name is Sudhir Vempati. I belong to the Department of Center for High Energy Physics, Indian Institute of Science. This course, and welcome to the course. This course is on quantum mechanics in the relativistic regime. Quantum mechanics relativistic regime. And as I do always, I will also give you my Sudhir Vempati. I am in Center for High Energy Physics, which is also called CHEP, Indian Institute of Science, Bangalore, and you can find my email ID and everything in the website essentially. So, as advertised, this course is on quantum mechanics in the relativistic regime essentially. So, this course will deal with quantum mechanics of particles which are travelling at speeds which are of relativistic velocities. And so what we will do is, the prerequisites of this course are both quantum mechanics in the non-relativistic regime and also special theory of relativity. Now, I will assume that most of you know these two topics, quantum mechanics, non-relativistic quantum mechanics or quantum mechanics 1, which you know at the level of Schiff or Merzbacher or one of these standard textbooks, and also special theory of relativity covered in various classical mechanics books and or book of Landau's theory of classical theory of fields. So, at that level I would assume that you know the topic. However, for completeness, what we will do in this course in the first two lectures is recap all the salient features of non-relativistic quantum mechanics, and later on in a couple of classes later I will also recap the salient features of special theory of relativity, so that the course is complete. And just to refresh our own memory about non-relativistic quantum mechanics, and I will be, while I am doing this, I will be sort of focusing only on those topics which are relevant for our course. Say for example, today I will be doing some basics of quantum mechanics, non-relativistic quantum mechanics, and the examples I will take will be revisited again later on in the course. So, to study what happens in the relativistic case. So, let us try to pay attention to these topics, which even though you know all this material very well, in the recap also I want you to focus on them, so that it will be useful when we revisit these topics later on. So, as I said, let us start looking at recap of quantum mechanics. When I say quantum mechanics, I mean here non-relativistic version. Incidentally, 2025 is 100 years of birth of quantum mechanics. So, this is the year when Heisenberg wrote his famous paper 100 years ago. In 1925, Heisenberg introduced quantum mechanics as matrix mechanics. Okay. We will come back to matrix version, more modern version of this matrix mechanics later on. Okay. But what we are more familiar, the books which you study and everything, happened next year, corresponds to the next year, when Schrodinger introduced something called the wave mechanics. So, today this is something which we are all familiar with, what we study by quantum mechanics. Essentially what we mean by quantum mechanics is, this is what we mean essentially, we study wave mechanics. So, let us start with the recap of wave mechanics. So, the fundamental principle, beginning point of wave mechanics is wave particle duality. When Planck and Einstein proposed the particle nature of radiation, proposed particle nature of energy or radiation, which led to understanding of the black body spectrum using the Planck's law and also photoelectric effect by Einstein, a question arose, what happens to particles essentially. So, de Broglie proposed the concept of wave particle duality. So, what he meant by the wave particle duality is that there is a matter wave associated with every particle. So, even matter particles will also have waves associated with them, and their wavelength is given by lambda. The wavelength is given by h cross, which is your Planck's constant, and mass of the particle and velocity of light. So, h cross, which will h by 2 pi, h is the Planck's constant, c is the velocity of light in vacuum, m is mass of the particle. So, the question immediately arises, if particles themselves have waves associated with them, or they behave like waves, these waves should satisfy a particular wave equation. Okay. So, these waves should satisfy a particular wave equation. So, what is this wave equation? Okay. What is this wave equation? So, wave equation for matter waves, this was answered by Schrodinger by Erwin Schrodinger in 1926, which goes under the scheme Schrodinger's wave equation. This goes under the name Schrodinger's wave equation. Now, when can you can directly write it down, but there is a easier way of remembering or deriving the Schrodinger's wave equation essentially. Noting that you can write the derivative forms of energy and momenta, okay, and then substitute them in the mass energy relation, and this gives you the Schrodinger's wave equation. So, for example, these are essentially the quantization conditions essentially. So, let us take P bar is equal to minus I h cross del, which is the quantization condition for a momenta, and then energy can be written as a derivative operator, there is a h cross Okay. Now substitute this in the energy momentum relation. E is equal to p square by 2m plus v. Okay, there is I del by del t, sorry. So, this is the non-relativistic energy momentum relation, where p square by 2m is the kinetic energy, v is the potential energy, and E is the total energy. Now, substituting the derivative forms of momenta and energy into the above equation and expecting that the wave should satisfy this condition, because it should satisfy, it is a matter wave. So, it should satisfy the energy momentum condition of the particles essentially. So, the matter wave should satisfy this energy momentum condition. So, this gives me I del by del t psi, which I represent the wave is equal to minus h cross square by 2m del square psi plus v psi. This is the so called Schrodinger wave equation. Now, here psi is essentially the wave, which is also called wave function. We will come to that essentially in a second, of the matter waves. So, any psi which satisfies this should solve is a quantum mechanical system in which you solve this and get the energy momentum conditions in a quantum mechanical system. Now, simplest solutions, let us look at them. Okay. So, the simplest solutions, simplest case case would be the case when V is equal to 0. You just set V is equal to 0 and that gives you the wave equation for a free particle. For a free particle, and which can be solved easily, and these solutions are called plane waves. So, the solutions when V is equal to 0 are called plane waves, which essentially are given by psi of x is equal to e power I k x, where k is equal to p by h cross, essentially, where k is equal to p by h cross. So, what we have seen is that there is one of the first concepts we have seen for quantum mechanics is the wave particle duality, and for every matter a particle, essentially there is a wave associated with it, and this wave satisfies something called the Schrodinger equation, Schrodinger wave equation, which we have just written down using the quantization conditions on momenta and time, essentially momenta and differential operators of the time of the energy. Given this condition, now we have seen that plane waves, the matter waves for a free particle are plane waves. So, that means they are not localized anywhere in nature. So, they can be anywhere essentially, and because in the absence of potential they need not be localized. So, now we look at some other concepts, related concepts, which are also equally important, and the first one is called the principle of superposition. What does this say? The principle of superposition says that if there are two different solutions of the Schrodinger equation, the sum of the linear combination or the sum of the two solutions is also a solution of the Schrodinger equation. Say for example, if psi 1 of x is a solution of Schrodinger equation, SC is Schrodinger equation, and independently psi 2 is also a solution of Schrodinger equation, then one can argue that if you have a psi of x which is a linear combination psi 1 of x plus b psi 2 of x is also a solution of the Schrodinger equation. So, that means that also describes the same particle, essentially same system, and this principle is one of the most important principles in quantum mechanics, which is called the principle of linear superposition. Okay. And in reality what we do is actually we often deal with not single waves or waves, but what we deal are a collection of waves, a small collection of bunch of waves which goes under the name wave packets. So, these wave packets describe the position of the wave, essentially roughly the probability of finding the particle in that particular direction, in that particular region. When you have the probability region, probability description of in quantum mechanics. Equally in the momentum space, what is the probable region of momenta or probable momenta the particle can carry, essentially. So, this wave packet have a spread which is given by delta x in the position space and say delta px in the momentum space, and they are constrained. These positions are not completely these widths are not completely independent, they are constrained by so called another important principle of quantum mechanics, which is called the uncertainty principle. We will come back to the uncertainty principle again, where these widths delta x delta px are bounded by h cross, essentially bounded, and the minimum uncertainty wave packet is the so called Gaussian wave packet. Okay, maybe the h cross is not visible clearly. The minimum uncertainty wave packet is the Gaussian wave packet, which is an exercise which you can do essentially. Now, we will come back to the uncertainty principle later on while dealing with measurements and probability interpretation in the coming class essentially. Okay. So, there also this plays a very important role essentially. Another important point of waves, okay, is the continuity of the wave function. Okay. Continuity of the wave function and its first derivative. Throughout the region of interest, we always insist this concept is very important while trying to solve the Schrodinger equations under various potentials essentially. Today we will see an example. Okay. This is extremely essential to solve the Schrodinger equation, because remember it is a second order differential equation and it requires two boundary conditions, one for the wave function itself at specific boundary points and another for the derivative essentially. So, the wave function and the derivative should be always continuous. Say for example, you can express it in that psi of x at any point x at x equal to a should be continuous at x plus epsilon, x goes to x plus epsilon essentially. So, you make sure that under any barrier here at a is equal to at x is equal to a you can have a potential, or we will see an explicit example in a couple of seconds in a couple of classes essentially, perhaps in the next class itself. So, and psi prime of x at x goes to a plus epsilon. Okay. Epsilon is a very small deviation essentially. Finally, before actually looking at some examples of potentials, one final point I want to distinguish between the kinds of solutions we are looking at in Schrodinger equation and in this particular case. So, psi prime is essentially the first derivative, okay, by the way, just to make it clear. Okay. So, there are two kinds of solutions for the Schrodinger equation, and one of those things are essentially called the scattering states. These are states which are not bounded by the potential essentially. So, they have energies typically larger than the potential energy of the system. Okay. They have their energy is always positive, okay, and these are called scattering states. So, these they are not bound to the system, they are not localized to any potential point. So, they are not localized in any space time point or anywhere nearby essentially, or in a region of space time point. Other ones are called the second set of class of solutions goes under the name as bound states. So, bound states typically here have energy less than V0 and they have negative energies. They are localized to a specific region of space depending upon the potential essentially. So, depending upon the potential. So, these are the two main classes of solutions we typically look when I am trying to solve the Schrodinger equation in various kinds of potentials. So, just to recap, so what we have done today. So, what we had tried to do today was to recap what is quantum mechanics in the non-relativistic case. We covered essentially wave mechanics, the salient features of wave mechanics. So, in which we covered the wave particle de Broglie's wave particle duality. Okay. So, wave particle duality and then which led to the formulation of the Schrodinger's wave equation, and which we derived essentially, or we wrote it down in this particular fashion essentially. Okay. And this wave equation has any quantum system should satisfy this wave equation, and now we can apply it to various atomic systems and simple atomic systems and various cases, various potentials, which we will see an example of in the next class essentially. Now, before doing that, we also revised the salient features of this wave. So, the first one of the main important features of this wave is that it satisfies the principle of superposition. If psi 1 is a solution of Schrodinger equation, psi 2 is also a solution of the Schrodinger equation, the linear combination where A and B are some constants. So, here A and B belong to, say for example, some complex constants. To see the sum A psi 1 of x and B psi 2 of x is also a solution of the Schrodinger equation, and this is called the principle of linear superposition. Similarly, we also looked at wave packets. So, wave packets are combinations of waves essentially, which are given by a spread in x direction is given by delta x, and spread in momentum space is given by delta px for one dimensional systems, and through which we introduce the uncertainty principle by introducing it as delta p, the spread in position, and the product of the spread in position and the product of spread in momentum is always bounded by below by h cross essentially. And the minimum in uncertainty wave packet is the Gaussian wave packet, which we will also do it meaning in great which we all know essentially, I guess you all understand, but anyway we will do it in we will introduce it later on, where delta px times delta x is equivalent to h cross. And finally, continuity of the wave function and its first derivatives at every space time point, the wave function and its first derivative should be continuous. This is true in every space time point, and then the classification of the two kinds of solutions which we can have for Schrodinger equation, which are the scattering states and the bound states. So, with this we have sort of covered the basic requirement to start solving the Schrodinger equation. So, in the next class we will take a very specific example of for the potential and to try to solve this Schrodinger equation, and then this is a prerequisite to do it later on in the relativistic case essentially. So, this is a non-relativistic this thing. Okay. So, I will stop here essentially. Thank you.